Alrighty, we'll get it going. I'm not giving too much of the presentation today, but I'm Daniel. I work in Markforged in product marketing, but I'll introduce these two here. So Ross is from Markforged. Ross, your title is Business Development Manager for binder jetting, but Ross has had about 6 titles this time here. He's worked all over our product line from doing application engineering work on our composite printers to being the product manager for our Metal X Metal FFF printer to now doing binder jetting, which he's done for about a year. His role is kind of a hybrid role where he prospects new applications, helps our customers, finds new prospective binder jetting folks, and then works with people like Cody, who is the general manager of Azoth, who is our largest customer in North America, has been with Markforged and then Digital Metal, the company we acquired since long before we have been involved in binder jetting, has a real expertise and has done some stuff with binder jetting, especially in the automotive sector, that very few other people have. So yeah, it's my pleasure to introduce these two and let them talk about what binder jetting is, how they use it, and some cool applications. So yeah, with that, we'll get started.
Awesome. Thank you, everyone. Got a really exciting agenda today, some great slides to share with you. And what Daniel failed to mention is it's his birthday as well today. So maybe at the end, we can all unmute and sing happy birthday to Daniel. All right, I'm going to share my screen. Why don't we get this going? All right. So what we got today is talk about metal binder jetting process, the applications that we're using it for, and we invited our special guest, Cody Cochran from Azoth, to provide some testimonies and talk about what they're doing in their business. So like Daniel mentioned, I'm the business development manager for the metal binder jetting segment of Markforged. I've been at this company for about 5 years, and I've never had so much excitement before than once I started working on this product. I have a ton of conviction in the metal binder jet process, and I really think it's going to be the inflection point for the 3D printing industry into more mainstream and use applications. Cody, do you want to give yourself a quick introduction?
Yeah, sure. My name's Cody Cochran. I'm the general manager, one of the co-founders of Azoth. We started it in 2017. We're based in Ann Arbor, Michigan. We have a focus on small, complex metal parts. Excited to chat with you guys today.
Sweet. So if you're familiar with Markforged, you probably have some awareness of our product portfolio, really well integrated into the FFF segment of the market. What I love about our portfolio is we've really spanned the 4 key application categories, from prototyping, tooling, spare parts, and ultimately end-use parts. What we're really going to focus on today is the metal binder jetting segment, of which is the PX100. This was an acquisition that we did in August of 2022 from the Swedish company Digital Metal. And we are integrating this company into our portfolio. And we're really targeting that end-use market segment for additive manufacturing. So above all else, my mission for this project here is to establish metal binder jetting as a production manufacturing process, and do so having it widely adopted across diverse industries. We take a step back and achieve this goal, we'll be very proud of what we've done for the 3D printing industry and ultimately for the whole manufacturing industry. Got to make meaningful impacts and make it a production manufacturing process. This is what we're laser focused on. So there's 3 key objectives for today's webinar. First one is to educate you on what the metal binder jetting process is, how it works, and then what are the unique advantages of this manufacturing process. And second is to help you identify what suitable applications are for metal binder jetting based on some characteristics and some parameters that we feel are the right fits that go into the sweet spot. And then lastly, we want to put you on a strategic evaluation path. Where do you start? How do you evaluate it? And how do you de-risk your investment to make the most value out of this unique manufacturing process? So that's what we got in store for today. So why don't we start with the process overview? How does binder jetting work? What better way to do that than sharing this video, Cody, talking through.
So what is binder jetting? The way it works is you're going to lay a layer of powder, in this case, roughly 42 microns thick. And then after you lay that layer of powder, you selectively deposit binder in the cross section of your parts. And we'll continue that over and over until we build up the entire Z height of the components. Once we've printed, we'll go through a curing step, which heat activates the binder. Basically, it locks all the metal powder into place. After that, we'll go through a depowdering step. So we can check that out over here. During depowdering, we're gonna blow off all the loose powder on the components. Then we vacuum that up to be recycled and reused in future prints. And when they're done with depowdering, it reveals like a green geometry. And a green geometry is about 20% oversized in every direction. We can then take that to the furnace for sintering. Sintering is a thermal process where basically we heat the parts up to just below their melting temperature. The parts will actually densify in every direction, and out comes a fully dense metal part. It's about a 20-hour cycle. The first segment, we remove the binders from the part. The next segment, we ramp up to near top temperature and hold for a prescribed amount of time. The parts will shrink roughly 20% in each direction, and then we'll cool down. At that point, the parts are ready for their next operation. A lot will ship as is, but some of them will go out for post-heat treatments. Some of them will go out for different surface coatings like chrome plating or PVD coating or Cerakoting, and some of the parts will go on to polishing.
Hopefully that gives you kind of a brief overview of how this process works. It's really simplified in the steps of print, depowder, and sinter. We're standing on the shoulders of a lot of science that's been established with metal injection molding on sintering. And what Markforged is very focused on is building the best printer in the world, putting the best green part into that furnace, establishing the best quality, and getting the outcomes of parts that you can put into production. We're very proud of this machine. We focus very heavily on the precision machine design, and we believe the tenets here are quality, reliability, and repeatability, the things that you absolutely need in order to go into production and do so in a way that you can launch products and keep the printers running with maximum uptime. This thing's built around a granite base, linear motors, air bearings. Granite base is very important because it keeps it very heavy and dampened to the forces of vibration. It keeps that powder bed very uniform across its density. Linear motors, this is a decision rather than using stepper motors and belts and pulleys to translate rotary motions to linear motions. It's how we get really good quality on our parts and have positional accuracy of 1 micron tolerance there. And then air bearings, this is very low wear, very low friction, but more importantly, when we talk about loose metal powder, the risk of contaminating that powder into a ball bearing, that's going to deteriorate your results over time. So our platform is entirely suspended by air, and that allows it to be running with very high uptime. We have printers in Sweden that have been running for over 10 years now, and they're still making production parts. So now that we know a little bit about the metal binder jet process, let's talk about the advantages that this process affords. So when I kind of zoom out, I think there's 4 key things about the metal binder jet process that sticks out amongst other types of metal 3D printing processes, all that lead it into this direction of serial production end use parts. So the first one we're going to hit on is the high throughput. Nothing really competes with binder jet in terms of throughput and speed. And the key reason there is that we're using an inkjet print head and the time per layer is constant. Regardless if you have 1 part or 1,000 parts in that cross section, it takes the same amount of time. We don't have to trace it. We don't have to draw the geometry of the part. So we can produce hundreds or even thousands of parts per day, a really efficient process to create green components. And then number 2 is cost effective. So because it's a high throughput process, we get really good economies of scale, and that leads to commercially viable cost per parts. Very critical when we're talking end use production. And that allows us to be viable in very demanding industries, automotive, consumer electronics, luxury goods, things that you can't launch products unless you have the right commercial requirements that you can achieve. And number 3 is going to be excellent part quality. The surface finish, the feature fidelity, get really smooth surface finish, about 6 micron RA values, and we can post-process that down to 1 micron to get really, mirror surfaces. And the material properties, they're isotropic. They're uniform across the entire part. We are able to operate to the same standards of metal injection molding, MPI F35, and that allows for much more predictability and repeatability of the integrity and the properties of the parts that you're getting and having that scale across thousands of components. And then lastly is very wide range of design freedom. I've seen some absolutely incredible parts made with binder jetting. Because of its resolution, there's no supports also in this process. So you don't have sacrificed surface finish. You don't have extra post-processing to consider the scalability of the process. And even greater is that there's no tooling involved in this process. So whenever you want to change the design, or if you have a high mix of different designs, You can scale that across a bunch of different components and do it all in just a single build box. So high throughput, cost effective, excellent part quality, and wide range of design freedom. These things all steer towards end use parts and demand an innovation in product design. So now let's talk about how we identify applications for the metal binder jet process. Just talked about what it's so great at, but there is some limitations there, and we want to really operate in a specific sweet spot. So if you ask me, Ross, what's binder jet good for? I would tell you this one single sentence right here. Metal binder jet is ideal for small, complex metal parts in mass production. I'll probably repeat that like 10 times throughout this presentation. Ideal for small, complex metal parts in mass production. This is what we're really focused on and what we think we do better than anyone else. But the engineer in me, has questions, right? What is small? What is complex? What is metal? And what do you mean by mass production? So for the next few slides in this presentation, we're going to dive deeper into what we mean by these notions. So starting with small, I typically say smaller the better. And the reason there is that we get higher throughput. With the higher throughput, the cost per part becomes improved. And even the dimensional accuracy gets better with smaller parts. Because we shrink about 20% during the sintering, basically the larger the part, the larger the shrink. And we get better accuracies with the smaller components. So to get more definitive there, the ideal parts are about 25 millimeters or 1 inch or less in the longest direction of the component. We love these parts. These are really good fits for the technology. You can get really high throughput. The cost effectiveness is very strong. We get really tight tolerances. Now we can't go bigger, and I'd say about 75 millimeters or less is the sweet spot. When we're below that, we definitely have something here that we can go and evaluate and have high confidence that we have the right technology fit for that type of geometry. Now, when we talk about the limits, the lower limit we'd like to say is less than 2 mil or greater than 2 millimeters. That's mostly a challenge of the depowdering process and being able to grab the parts and move them around to the next step of the process. We can go a little bit smaller, but 2 millimeters is a good governing factor. And then the absolute upper limit here, we say is about 150 millimeters. This is going to be a balance of high part cost, loose dimensional accuracy needed in post-machining. In demanding applications, we've certainly done parts up to this extreme, but it requires a little bit more scrutiny when we think about the business case and if this process still makes sense at these types of part sizes. So, 1 inch or less, we got something great. Less than 3 inches, we're on the right track. And then these two extremes, we want to stay within. So small parts, smaller the better. Now let's talk about complexity. More complex, the better. Now, intricate features, either challenging or outright impossible to achieve with traditional manufacturing methods. We often see parts made through CNC machining, metal injection molding, investment casting, and laser powder bed fusion being the incumbent metal 3D printing process. We like the impossible features, things that no one else can do in any other way. And the type of aspects that we see here are lattice structures, being able to lightweight the component, being able to put filtration designs into the component, and doing that conformal with inside it. A lot of great opportunities for lattice structures, and we can go down to like 200 micron bead thickness on these struts. Internal channels, these are fantastic applications for 3D printing, being able to be more conformal to the design, the geometry, being able to have more smooth transitions throughout it and not needing supports makes these type of applications really good fits for binder jetting. The next one's going to be consolidated assemblies. These are great opportunities to take part count and bring it into a single monolith component. I often encourage people not to just look at the single application, but to zoom out and look at the subassembly. And usually when you take a view in that perspective, you start seeing more opportunities to consolidate multiple parts into a single feature and extract more value that you can get otherwise. We really need to engineer value into the parts, and that's where you're going to see the best benefits of binder jetting and have the best opportunities. But impossible features, those usually don't exist. We need to encourage people to push the limits and get them thinking differently. But our starting point is usually these challenging features within the realm of traditional manufacturing. For thin contoured walls, these are good parts to replace CNC machining and reduce the amount of time that it goes on high value CNC machines, because you're using really small end mills and you have really light work holding so you don't deform the component. These are great types of applications that we can investigate and see if we can improve on cost level. Number two would be difficult materials. And the ones I highlight here are pure copper and nickel alloys, things that are really hard to shape, really hard to machine, really hard to cast, really hard to weld. The benefit of sintering is it eliminates some of those challenges, and being able to scale from like a stainless steel to a copper material within this process is very seamless. And then the last one's going to be high product mix. Being able to have a lot of customization, being able to manage a bunch of different SKUs and different types of geometries. Cody's going to talk a lot about this and what they're doing in the automotive industry. But because there's no tooling in this process, we allow customers to scale much more organically and test out different concepts and designs and have a variety of different offerings in their product portfolios. So that's kind of what we talk about when we say complex parts, either impossible or challenging. We like impossible because it's possible with us. Okay, into the metal. Basically any metal powder that you can sinter, that's theoretically possible with metal binder jetting. Oftentimes it's not just the design, but it's the material itself that can lend itself better to using this type of manufacturing. There's a lot of different materials. We have some customers that have qualified their own materials because our system's open architecture. But the ones that we're focused on today and that we've already qualified include some general purpose stainless steels. 17.4 and 316L would be your most popular there. The right blend of strength, corrosion, wear, heat. We're seeing a lot of traction in those type of stainless steels. We also have 4140, low alloy carbon, a little bit tougher of a material. In the high performance realm, we got pure copper, about 99.9% pure, very good thermal and electrical conductivity. Also antimicrobial applications are very interested in that, as well as titanium for very high strength to weight ratio, very good corrosion resistance, very demanding applications there. Super alloys are very exciting, particularly for aerospace, oil and gas, and those types of industries. Two different flavors of Inconel, 625 and 718. We're also very excited about this MAR-M247 material because this is something that you can't actually use in laser powder bed. It doesn't like to be welded together, but lends itself very well to the sintering process. And then finally, two different types of tool steels, H13 and D2. We're seeing a lot of applications for types of punches and dies, and where hardness is really required and critical, we have tool steels to address those type of applications as well. So about 10 materials on the screen here, and we're constantly evolving and adding more. And definitely love to hear feedback from customers of what materials we're missing as well. Now into mass production. The mass production aspect really depends on the size of the part. That's going to be your governing factor of how many parts you can put into a build box and route through the entire process. I made this chart right here just to articulate if you have a bounding box of a certain size component and you have one PX100 and you're operating that at about 80% uptime throughout the year, you see the million parts per year threshold come in at about a 10 by 10 by 10 millimeter cube. We can produce 2,600 of those a day, really high throughput in that perspective. Of course, everything scales linearly. As you add more printers, you can increase that throughput and chase those types of volume requirements. But again, smaller the better, as you can see from the annual volumes. And of course, cost corresponds with this because of the equipment amortization at high volume economies of scale. So once again, metal binder jetting is ideal for small, complex metal parts in mass production. We made this very nice one-pager that we'll follow up after this webinar and provide everyone as a reference piece of material. Because if you have a need for small, complex metal parts in mass production, we really feel strongly that you should be looking at metal binder jetting and evaluating are there opportunities that you can utilize this process and extract new types of value through engineering, design, and ultimately innovate inside your products. So what about strategic evaluation? We talked about how the process works and some of the equipment that you need. And a question I often get asked is, should I make parts or should I buy parts? And it really comes down to where you're at in your additive journey, what type of risk tolerance you have, and how you're trying to enter these opportunities. So when you have a need for small, complex metal parts, we have two different paths here. If you're ready to implement metal binder jetting, but not ready to make the investment, we have contract manufacturers like Azoth, who are really great partners for you to go onto this journey, start getting parts made and bring them into applications. While if ultimately leading towards the investment of the machine when it comes into ROI analysis. Of course, I'm here as well to help you adopt the technology. And we're not just here to sell you printers, we're here to sell you a solution and ensure that your success is realized through a training curriculum and service and support on top of the world's best metal binder jet printer. So this is a concept that we talked a lot about because it's very important to go at the customer's pace. And I want to hand it over to Cody to talk a little bit about the way Azoth partners with their customers and what some of the successes they've had within their binder jet operations.
Awesome. Thanks, Ross. Great overview so far. Really enjoyed that. Helpful. Wish I would have started with that information myself. So, little background on Azoth. We are based in Ann Arbor, Michigan, and we focus on center-based additive manufacturing, binder jetting. We also have a leading digital inventory solution. We call it Take One, Make One, Tomo, where we help industrial manufacturers set up 3D printing in their facilities and utilize a digital inventory that can be printed on demand. So we support over 40 different polymers in addition to our metals offering for that. Our primary industries that we are making metal parts in today are automotive, medical, defense, and the luxury goods segment. And I think really what makes us different than a lot of other companies in the 3D printing space is our focus on manufacturing. We're a manufacturing company. Our medium of manufacturing just happens to be 3D printing. We're focused on a production part approval process, going through the drawings, setting up tolerances, GD&T that's specific to our process, and helping our customers launch serial production components. We're not a service bureau that's going to, just take your file, quote it as a one-off, print it and ship it to you. We're really going to go through how do we launch this new product and go into serial production. And that's our focus. Next slide. I'll talk a little bit about our path to share how we got into center-based additive. If you're interested in adopting it in your company, it may be helpful to know our path to get into this as well. So with our Tomo digital inventory model, of course, we supported over 40 different polymers, and most of our customers' feedback for us was, we love this business, but we wish you could do it out of metal. We want tool steels. We want stainless steels. And so for Azoth, we chose to utilize binder jetting in a relatively high product mix at lower volume environment for the tooling, jigs, fixtures market. We felt that additives totally ready for the tooling, jigs, fixtures market since 2017 timeframe when we started it. And so when we launched binder jetting for this market, we really became one of the first contract manufacturers in the US that is vendor neutral, utilizing binder jet for contract manufacturing for a variety of customers. And that was a really good place to start. You can see a lot of the pictures along the right there are gripper fingers and the barn details, part locators, and more of traditional designs that you would use in tooling, jigs, fixtures. Used to be primarily machined. As that evolved and we developed a market presence with our technology, we found a lot of customers coming up with ideas for what I would call end-use products. And we made that transition from tooling, jigs, fixtures into higher volume components, customers that needed hundreds of parts at a time, primarily for what I would call the rapid product development market. And so we were really winning on three different core principles at that point in time. People would come to us for speed to market. They would look at designs that are metal injection molded or investment cast or machined, and they would say, I have 3 to 5 product iterations before this thing's going to be ready. I don't have time for tooling every step of the way. Our business model usually has parts out the door in 10 to 15 days. And so we utilize binder jet, help people get their product to market faster. And that kind of goes with cost as well. Obviously, there's a cost potential if you can launch new products faster, but there's also a tooling avoidance for utilizing this technology, especially as you're going through multiple iterations. And then obviously the holy grail for us is when someone really designs for this process, as Ross alluded to, complex features with internal channels or part consolidation or mass customization. Hey, I want to serialize components. That was the next market that really started to pick up for us. And I think, I'll reiterate, the key is always that we find people aren't necessarily looking for prototypes. And that's really great for this technology. We find people want to launch new products, and to be able to go through the product development phase and then into production on the exact same piece of equipment and not have to switch technologies has been really useful for customers. So make the first 5 parts 10 different iterations of it, and then, you know, go to 20 parts, go to 100 parts, and then be able to utilize all that data and say, let's go to thousands of parts per month, is really nice to not have to switch technologies. And so our business definitely evolved from tooling, jigs, fixtures, focused then on more traditional designs for additive. And a big win for Azoth early on has been what I call the bespoke automotive components. And that's really evolved into a large automotive presence for Azoth today. And where we see people using it in the automotive industry is high value components you get in the vehicle and say, wow, that's really awesome. It adds some kind of tactile experience. High polished 360 ounce stainless is a very common one. I'll show you many examples of where we're utilizing that technology. And now today, I mean, Azoth, you know, 70% of what we're focused on is our serial high volume production. Repeat customers that we have contracts with, that we owe parts every month, that we've completed a PPAP package, gone through their corrosion testing, gone through mechanical testing, part specific testing, certified the process, and we make parts for them every month. And that's really the best use of this technology, is making parts that are difficult or can't be really made with other technologies, and doing that at scale. So I'll share a few of those examples throughout this slide to get some people's thoughts going. The first component that I'll share is we actually launched the first metal 3D printed part for a production vehicle with General Motors. That was on their Cadillac Blackwing. It's a tribute to the last manual transmission that they'll be manufacturing. So we actually did this 316 ounce stainless steel shifter insert. It's high polished with a brushed finish across it, so very high detail, a tribute to, you know, the Blackwing itself. And that was an awesome component. It's definitely more of a cosmetic component. It's vehicle jewelry is the way I describe it. But what's really was a milestone for Azoth at the time is that it still had to go through a full PPAP process. We still do very advanced corrosion testing for the automotive industry, dimensional layouts, and going through, you know, your PFMEAs, your DFMEAs, and really making sure that you can make this product time and time again for the production length of that vehicle. So when binder jetting passed that, it really opened up the doors for many other applications at Azoth. Today, we have over 40 parts with a full PPAP, including some safety critical components. And we're doing that across 12 different tier ones and OEMs throughout the automotive industry, which is really awesome for me, and I think awesome for the industry, because when these tier one automotive companies are coming in and they're auditing the process and they're bringing new process engineers with a different set of different lens and different set of questions as they're going through our shop, and to build trust across that many companies and say, yes, your parts are certified, we can make them in production. I really think cosigns on this being a scalable production ready technology. So I'll go through some other applications. Some of these are aftermarket, most of these are aftermarket automotive, not necessarily the tiered automotive supply chain going direct to OEMs, but it'll show some mass customization and some advantages we can do. Like these Jeep shift knobs, we, you know, designed in the Moab Mountains background into them, so they have a nice contoured background, playing on the benefits of additive. High polished 316 ounce stainless steel with a textured background in the back, so we have multiple different versions of that we enable our customer to sell online for the transfer case and shift knob. If you go to the next one for me, Ross, we've done some really cool limited edition runs with binder jetting technology, Jurassic Park serialized editions, and this shows just some of the fidelity. You can see the resolution we're able to get on the part, but it also shows, you know, that ability to help customers enable mass customization for markets like Jeep owners who really appreciate that. Some further examples, you know, you can see more variety where we are able to apply different kind of surface coatings. So common surface coatings for cosmetic components would be PVD coating. That's how we get the gold look, or the really shiny black look on some of these components. We can also utilize Cerakote, which is a really durable, robust material, or a robust surface coating to get that black background you see on this component with a high polished front surface. So really bespoke applications, but applications that really are adding some kind of value to the vehicle. Some of my favorite ones, you know, we had this horn button on the carbon fiber steering wheel. It won at SEMA's Battle of the Builders with the Ring Brothers group. But, you know, starting with a sketchboard and all the ideas, Azoth is able to help our customers walk through the design ideation phase and get physical parts in hands to see the variety, and then actually make these into production, right? So you make your initial prototypes, customer selects their favorite, and then to be able to launch these. So lots of different options here. This is some aftermarket perspective, but what I'll say is that, you know, anywhere you touch, if it's a button, a knob, a handle, we are really doing some awesome things with stainless steel in that market. Outside of the automotive industry, another big industry for Azoth is defense, working on really complex components like this fluid matter exchanger. This won the grand prize in industrial motors and controls at the MPIF conference last year. And what I love about this component is we help the customer consolidate what used to be 40 different machined components that got brazed together downstream into one additive manufactured component. And so that was a really awesome milestone to see for Azoth as a company, to be able to help a customer consolidate 40 different pieces, which is, you know, a pretty large supply chain, the assembly process to put those all together, and then to really make a robust design where it's now one 3D printed component. We're able to do multiple internal channels, internal filters, internal features that previously you really couldn't machine. Obviously, you had to make it 40 different parts and bring it all together. Very thin-walled component. This is actually about 90 millimeters tall, so it's a rather large component for binder jetting. And, you know, we're going down with like M1.2 threads in some area that we're actually able to print into the component. So that was a huge milestone, and you can see the evolution as you start to adopt this technology, working with tooling, jigs, fixtures, what might look like 3-axis machined components, and then you go to what look like 5-axis machined components, and then eventually you get to really what I would say is our holy grail, and it's, hey, this is designed for the process and brings a lot of function and value to our customers. So a lot of awesome applications like this in the defense space. You know, other applications include antenna structures, which have a lot of small complex features that typically, if you were to make an array, you really couldn't nest so many of those kind of geometries into the small footprint you're able to with binder jetting. So great applications for us. And I'll kind of close on a question that I often get. A lot of the questions I see from new users of the technology, from people looking to get parts for the first time, and the questions that I had when I started to get into binder jetting is that they really boil down to, like, how do you build trust? You know, if you're going to use this new tech, it's new to your organization, it's new to you. How do you build trust in the technology? And so one of the things I like to share with people is that we do have an industry standard for our materials, MPIF 35, that breaks out the mechanical properties, the micrograph, and Ross alluded to it, but this is really old science based on metal injection molding, and we're applying a new technology to create the green parts. And so it's really nice that we have an industry standard to be able to look at the mechanical properties and share that with the customers. We utilize the same quality management systems. I mean, Azoth's ISO 9001, and we look to our aerospace work, AS 9100, medical, ISO 13485. As you look at those quality management systems and suppliers are able to put those traditional systems in place, that's what we're operating to as well. If you compare us to a known technology like metal injection molding, you can see the breakout in that chart there. We have we're operating to the same mechanical and chemical property standards, metallurgical microstructure. It looks the same if you're working with your metallurgic metallurgist, they're going to look at a micrograph of MEM and binder jet and know exactly what they're looking at. That's not always true with other forms of metal printing. So that's really nice when it comes to binder jetting. Very similar surface finish. At the end of the day, metal injection molding is going to be better. They're using a machined and sometimes polished mold and have about a 1.2 micron RA. We're usually somewhere closer to a 4 to 6 micron RA. Machine to surface or polish to surface is usually sufficient for the applications. And then as from a resolution standpoint, it's about 50 microns with this technology. Tolerances, when you really design well, we always say about plus or minus 0.5% or somewhere around 5 thou seems to be the typical tolerance on a well-designed part. On a one-off part that maybe hasn't had as much thought into design for binder jetting, but you want to get into it and get your first prototype. We typically see plus or minus 1.5% of the nominal dimension being a fair target to start with, and then dialing that in with better designs and future iterations. But one thing I'll point to that's always helped Azoth, the PPAPA component and develop trust, is that our variation follows a normal distribution throughout production. So you can see what we have a production example there across multiple parts, hundreds of parts, and it follows a normal distribution. We have very minimal process degradation. So when you look to PPAP apart and you look at, hey, what are my tolerances over time? Binder jetting does follow a normal distribution that a process engineer can put in reasonable controls and scale this technology. And I think that is, very promising as you look to PPAPing a component. So thanks, Ross. That's been our experience, and one of the major questions we get asked. Hopefully there's plenty of questions at the end of this that we can dive into and have some further dialogue in, and maybe dive a little deeper than the high level applications I shared.
Thanks, Cody. Yeah, great job. Ever since I started learning about all this vehicle jewelry, every time I touch the buttons on my car and feel the plastic part that's chrome plated, I just kind of get sad and want to start integrating more stainless steel like that. But it's great. Very happy to see all these applications, and now you got to start looking closer in the world. And when you see some metal parts, look for the layer lines. Look to see if they're 3D printed. I think more and more start trickling in, and I'm feeling very proud of that.
Yeah, absolutely.
So what we'll finish you off with is, a question I always get asked, which is, where do I start? Right. And I'm not really here to talk about printers. I'm here to talk about applications. And really my mission, right, is to make this a production manufacturing process. So what we've architected in partnership with Azoth is what we call our Start Smart program. The headline here is basically start smart with quality parts that are production ready. Doesn't matter how many parts we can make, if we can't make them at the quality, and we want to deliver to you something that's production ready, not just onesie twosies, but things that are ready to go into scale over time. So there's 4 key steps to this program. It starts with identifying the applications. So we gave you this framework, the small complex metal parts in mass production. Send us 20 parts. We want to boil that down to what are the top 5 parts? What's the top 1 part? And help you redesign that component to lend itself better to this process and start engineering that value that you couldn't get otherwise. Once we identify those applications and feel good about the path that we're on, we're going to go and validate it for you. We want to make sure that your dimensions are stable, that your chemical composition is withstanding the environment, that the cost of the component to produce with the metal powder and the binders and the sintering is going to be commercially viable for the ultimate goal of going into production. Once we achieve that, it comes into a make versus buy analysis. If we feel like the best place for you to start is to just purchase components and partner with Azoth, perfect. Cody's going to provide you a quote at production, and then they're going to start launching it. If we feel like it makes more sense to bring this technology in-house, control the process, and build up that expertise, I'm going to provide you with a proposal. I'm going to show you exactly what we're putting into that package and why we think that this is the right equipment that corresponds with your requirements. And then we're going to load that with services and support, as well as training, to ensure that your team members are experts in this process and are able to operate it into that production. So finally, it's going to launch production applications. And that's what gets me up in the morning, gets me very excited. Putting things out in the world that you produce and your customers are using every day that are benefiting from the 3D printing process. And it's a cycle. That's the beauty in 3D printing. It's continuous improvement. There's always more opportunities to either keep improving the existing design or look outwards and find new opportunities, new applications, building on top of that knowledge that you built up in the first round, and then scaling it to more applications. Capable of doing millions of parts, we're capable of doing the most complex parts, and our machine is robust and reliable enough that you can feel confident that it's going to work and it's going to be stable, and that you're going to be the hero at your company and doing things that no one else has done before. So that wraps up what we had for today. I hope everyone enjoyed it. Very high level overview of the binder gem process and why we think you should be investigating it. So we're ready to open up for some questions and answers and see what you got. So Daniel, you're gonna kind of MC this, but you can just talk through my mic and tee us up with some questions.
All right, yeah, I'll proctor this.
Thank you.
Super quick. And so just some housekeeping, I mentioned it in the chat. There's a Q&A section. If you have questions, please ask them through there. We also had a few that came in via email beforehand, so we'll start with that, and we'll try to get to as many as we can. Probably about 15 minutes of question and answer. But yeah, okay. So first question, asked about 4 different ways on this on the Q&A here. How does shrinkage work and how does it affect part dimensions? So I'll leave it to both of you to figure out exactly how to answer that, but I think the gist would be we're trying to make, we talk about precision parts, small parts, high quality parts, but obviously there's some mechanical change in parts post printing. How do you account for that? Does it change material to material? Can you still make precision machine components? Do you need to post process them? All that kind of stuff.
Got it. Cody, I'll take the first stab and then maybe you can complement what I say.
Sounds good.
Cool. So when we think about sintering, it's been around for a long time, and it's a process that basically uses heat induced with metal powder, and we reach about 80 to 90% of the melting temperature. We don't want to go to melting because then you create a puddle, but towards that sintering temperature, the metal powder begins to neck and occupy the empty space. And there's 2 key factors here that achieve the success. It's first is the density of your metal powder part. So we're about 50% by volume, and the amount of empty space is going to determine how much space it has to shrink into. Then the second thing is going to be the temperature and the uniformity of that temperature. So you want really uniform temperatures inside your sintering furnace. So from corner to corner of that, each part is getting the same amount of heat, and that's going to determine how much it shrinks and how the final properties are. So we partner with the best companies in sintering to make sure that we get the best uniformity, and we over-engineer our printer with high precision to make sure that we get uniform powder density across the build envelope. The net result is about a 96 to 99% dense part, depending on the material and the sinter profile that you derive. And of course, you can hit these afterwards to get full density if you need full raw properties. But overall, it's a metal part that you can machine, heat treat, polish, anything that you would do to a normal metal part.
Yeah, I think that's a great way to answer it. I'll give like a process engineer's perspective. We manage a set of very specific scaling factors for our components. These components get scaled in the X, Y, and Z by a specific factor for each material. So each material does have its own set of scaling factors. But, when we apply that set of scaling factors for a given material, I have a very high confidence level demonstrated over time that your parts are going to shrink per that scaling factor, and that's all within the window that I give. So when I say plus or minus 1%, if we set up your blueprint, all your tolerances on there, we would account for the variation across production and say we need a tolerance of X based on and it's mainly based on the size of your part, the size of that dimensional feature. And then sometimes if you have a really unique cross section, which plays influence into the densification, sometimes you have to do what we would call rescaling of the component, do some localized scaling for your specific features. We'll say about 10% of our parts need that. 90% of our parts we can apply like our general set of scaling factors that we maintain. Your part's going to come out great on the first time. But there are some really unique geometries out there, particularly parts that go from real thick cross sections with thin features on them. Sometimes we have to get a little bit more creative on how we scale those. But once you identify that specific set of scaling factors, the printers are very robust. The sintering equipment's very robust. You're able to maintain that and hit the tolerances every time.
Nice. Sounds good. All right. Next question. We talked a little bit about this in terms of the process, but someone asked what is the rate of reuse for powder used in the printing process, but not used in part fabrication. So it might be, I think maybe Ross and Cody spend a little bit of time talking about the life cycle of powder when it prints. Obviously, the answer is all prints have some portion of recycled powder, but you guys can go into more detail.
Yeah, when we think about like the sustainability of this process, that's also a lens to look it through because we can reuse all the unused powder. You don't have scrap like you would with machine and process. The benefit in binder jen is the high energy during printing is very low. The high energy rate happens during sintering where we're introducing the heat and densifying the parts. So we don't have like weld splatters. We don't have aggregates building up during the printing process. Everything can be recycled back in. Say 100%, that's theoretical. It's more like 99%. Some powder is just not worth chasing. The powder recycling process, you basically mix it at a 3-to-1 ratio of mixed powder with virgin powder. We sieve it through a set of primary and secondary meshes, and then we homogenize it, and then we heat it up to avoid any moisture building up. So yeah, I mean, full reusability of the powder. I don't know, Cody, you have anything to add or some of your experience running?
I mean, your refresh rate is kind of set on your average packing density. So how many green parts you're putting in there. Obviously those green parts are going to move down the rest of the process and you need to be able to replenish that. So your refresh rate is going to be around, it's going to be similar to your packing density and account for that. And like Ross said, I mean, since we're not adding heat during printing, we have a high reusability of this powder throughout the process. So that's really awesome with binder jetting.
Cool. Okay. Let's see. What's the next group of questions that we should ask here? There's a simple one, which is I've seen a couple questions about adding aluminum. I think for a few reasons, aluminum isn't really a material that we're targeting. There's kind of a couple like big picture things there. It's actually a relatively similar story for our metal FFF printer. Aluminum powder is notably very reactive and difficult to print with for a number of factors. It's also, of all metals, just about the cheapest metal to machine. So while it could be useful, I think right now it's not the primary focus. You'll see a lot more focus on these materials that are difficult to machine, difficult to work with, because that's where the greatest ROI comes with.
Yeah, I guess when you think of my slide about like which metals can we do, I did say any metal that you can sinter is theoretically possible. So aluminum's definitely possible.
It's possible, yeah, but not immediately. It's kind of
but then you think of the complex slide, and I said difficult to use materials. Well, aluminum, why you typically use it, it's cheap and easy to machine. It becomes a lot more expensive when you put it in powder form, and we're not machining here, we're sintering, which it's one of the more difficult materials to sinter. Yeah. But I'm hyper interested in learning more, so I will follow up with whoever asked that question and learn more about what you're thinking with aluminum.
I think there were 3 people who asked it, so you
got
to follow up. Okay, next question is like a triple question, all for Cody. It seems like Azoth has gotten a good rap from this. So through the triple question is one gentleman asked, I'm printing in the hundreds per year. Is that an acceptable volume to engage with Azoth? Another person asked, when you ask for providing prototypes, what's your lead time to provide parts? How do you engage? And the last one was, how do you get a quote and how do you get in touch? So those 3, Cody, I'll kick them all to you.
I'll start with how you get in touch. On our website, azoth3d.com, you click request a quote. You can upload your CAD files. If you know the process and material that you want, you can select it, select your quantities, attach your technical drawing if you have it dimensioned out with your requirements. And we typically are able to turn those quotes around in under 24 hours. You'll get a link with your file, your quantity break, your lead time, and check out online or upload a PO for it. So super easy to request a quote from us. Typical lead times on binder jet components range in the 10 to 15 day range. As you start to add some more extensive post-processing to it, let's say you need, some complex post machining, or you want a very specific polish, or you want the parts PVD coated, sometimes you'll get closer to 20 days, but 10 to 15 days is our average lead time on the new product development, prototype, or lower volume orders like you're asking about. And as far as typical volumes, we have customers that, still order 10 parts a year, all the way up to customers we're working with to make 1 million parts a year. So we have quite a range there. So if you're looking at a product line that has hundreds of parts, Yeah, the answer is likely yes. It can make a lot of sense to work with Azoth on those. We typically win in 3 areas. I always tell people, if you don't have a design that is specific to additive and you're taking away some of the benefits there, then we're looking at cost and lead time. So if you're machining it, you're in metal injection molding, or your investment cast, depending on the number of parts you have and the complexity, there's a different kind of equation for if we're going to win on cost or if we're going to win on lead time. But we go up against all of those technologies, and sometimes binder jet's the right tool to put in your tool belt and utilize over machining or MIM. Just depends on where you're at in the product life cycle and where you're at with needing tooling and what kind of volumes you're trying to make. So would love to look at the hundreds of applications.
I think we have time for maybe 3 more questions. I have one already loaded up, again, a multi question. So there's a kind of a triple question here about sintering. The first one is material strength about sintering compared to machine components. I believe I can answer that, which is it's near MIM strength, correct?
Mhm.
And generally, MIM is like a super well documented set of material property expectations. We're really experienced it from the Markforged non-metal FFF side because we're also near MIM for that. So it's about 90%, maybe 95% of rock strength, which is kind of the typical. And then there's kind of a bunch of maybe more design focused questions on sintering. So first one is, are there any geometries that are difficult on sintering? If there aren't flat surfaces, does it make it more difficult? With respect to high mix, what impact do multiple sinter rafts and sinter supports have on tooling costs? Are these printed with the parts every time? Are they reused, or is there another thing? Hint, hint. And I guess the last one, kind of sort of related to this, is there anything in CAD we should be mindful of when we're designing for anticipating metal printing? Things are all kind of in the same boat, but maybe talk a little bit about sintering and how part design and the difference between the print constraints and the sinter constraints.
Yep. Okay. We think about like the forces at play while sintering. You have 2 main forces. You have gravity and you have friction. Both of those are induced by the mass of the component, and that determines how much or how severe it is. When you have components that are kind of like, sitting like this, so if this is your flat surface, during sintering, it's going to want to slump over. It's going to want to collapse. You need what we call live setters that help control that shrinkage, keep everything uniform, and keep that body stable as it's going through that shrinkage process. They cannot be reused. They turn into a sintered metal part. We put an interface ceramic coating in between the 2, very low impact, removes the part from the setter. And we can get pretty creative with those. You can shave off a couple of extra features. You can put honeycomb designs to make them super lightweight, thereby reducing the material cost. And ultimately, when you go into production, and we really want to avoid these live setters, you can machine ceramic plates and kind of have these nested in different shapes that will be reusable and not have material costs associated each time that you do a furnace run. So it's definitely a part of the art of the binder jet. I'd say Azoth knows, so much about designing really cost-effective, reliable setters, and as well as, the CAD programming for it. Cody, do you want to talk a little bit about setters?
I think you nailed it. In the beginning, it's a nice reason to work with some people who have used the process before to be able to get you set up for a robust production process. I mean, with the setters, we use a live setter, as mentioned, that we print with the component. It shrinks with the component, so that's a one-time use. It results in a very dimensionally accurate part, and if you have lower volumes or you're trying to move quickly, printing a live setter is very effective. As Ross mentioned, as we look to like larger volume production, we don't want that extra piece to print or that scrap material involved with it. We do look at machine ceramics. If you do have a flat feature on your component, you can avoid a machine ceramic or a live setter if it's designed that way. That's super helpful. So there's a lot of kind of tips and tricks and different ways to sinter these components. There are some software simulation tools in the marketplace that can assist with it as well, and that's becoming more and more advanced. But at the end of the day, I would say, you working with the Markforged team, they do a great job of not just being printer focused, but being process focused, and it's pretty reasonable process to start designing your own setters. It's a robust process, and as you grow as a company with the technology, you can get more and more complex parts over time.
Awesome. All right, so it looks like the customer or the attendee questions have dried up, so I'm going to ask 2 quick ones. One's from me, and then one's from an email we got earlier. So first one, my question is for you, Cody. You kind of alluded to this in the presentation, but what is the one thing you wish you knew about binder jetting now that you know now after being in it for 5 years plus when you were acquiring the machines?
One thing I wish I knew. I would say the most impactful thing that we did is, just focus on adopting binder jet and with a supplier or OEM that has a robust process established for their equipment today. So, rather than just focusing on the printer or just focusing on powder or just focusing on sinter, it's the entire process loop and having robust controls at every one of those steps that really evolves the company, and I see a lot of newer groups reaching out to Azoth for support and launching binder jet, and they get really excited about launching new crazy powders or shortening sintering cycles or running different binders or running, how am I going to make this super complex part? But, working with an OEM that has a robust process controls in place, following that process to a T, and slowly developing experience over time to where you're comfortable running the process, and then start turning all the other bells and whistles as far as trying to make parts that nobody else can make with the technology. But, take it, there is a very robust process in place. You can adopt it with the controls that Markforged would put out to you, and use those in the beginning, and slowly your parts will grow more advanced. And you can see that in ours, right? I started with gripper fingers, and today we're making, that crazy fluid matter exchanger and parts that you can't even 5-axis machine. So start with the process that's delivered, and slowly it'll evolve to where you're making some really crazy parts. But that's probably my biggest tip. I don't know if there's any regret in there, but
I don't think there's much regret for you to have. And then I'll ask one last question to you, Ross, that came from an email, and to you a little bit, Cody, as well. But since Ross, you're the sales guy, you get to answer this one. Why choose Markforged over the other binder jet machines on the market?
I think the machine spoke for itself in the beginning. Granite base, linear motors, air bearings. I've never seen anyone in the 3D printing industry take that level of dedication to precision. I mean, when you're pursuing precision, you don't make any compromises. When you're chasing tight tolerances, these type of design decisions matter on our platform. And it's very proven. These are production parts that are meeting the automotive standards, that are doing things that people say you can't do with binder jet. And Azoth is a great testimony to the success that they've had with our machine. And when I'm just really proud that we acquired this company in Sweden. We're bringing them into our portfolio. We're trying to make true of the promise of additive, which is end use production, any type of geometry you can imagine, but doing it at high volume, doing it at scale, and making things that people are seeing every day in the world. So that's our mission: make it a production manufacturing process, have it widely adopted across diverse industries.
Yeah, I mean, from my perspective, I come from traditional manufacturing. When I seen the machine for the first time, the granite table, linear motors, air bearings, a full package of Siemens controls, that's what spoke to me. I said, wow, this is built like the equipment that I'm used to being around. So that was the first, walking up to the machine when I seen it for the first time, that really got me excited. As I've had experience with the technology over time, I like that it is built around a robust concept, that it's brand aligned, that we're going to make serialized production components. And it's nice working with a group that's brand aligned on that. And also it's nice working with a group that has really incredible subject matter experts that go to work and think about powder and printing and continuous improvement every day. I feel that they have an incredible team that supported Azoth's growth, and that makes a great partner in Markforged for us.
Thank you. Well, thank you all so much for coming. Ross and Cody's emails are on this. We also have all your contact info. I'm sure they'll be reaching out soon. It's been super informative. I hope y'all have learned some stuff, especially if you came from more FFF type world. Thanks for spending time with us today, and we'll reach out in the future.
Yeah, thank you, everyone. Excited to engage with you. Hope that this was informative and gave you a little bird's eye view into what Markforged is doing with binder jet and how we're thinking about this product. And I think the future is very bright, and very happy to be partnered with Azoth and Cody over on their business to help live up to this mission.
Likewise, thanks so much.
All right, everyone. Have a great rest of your day.